All right, welcome back to another video. I'm gonna keep going on chapter 15. So this is part 3 of chapter 15. Part 2, I decided to stop kind of early, only after half hour, because it goes over the idea that in order to reduce the costs it takes to manage an environment, you have to make the right technical choices. And one of the technical choices that you'll be faced with is which kind of database do I use for my product? So if you make the wrong choice there, you're always going to be having problems. And that's one thing I'd actually like to go back through and do this again. So, for example, if you want to if you're working with financial inventory, any system requiring accurate record keeping with complex queries, you have to use a relational database. And if you instead use a search engine, an in-memory database, a time series database, you're going to have you're going to have all kinds of problems. And likewise, if you're setting up a financial trading platform, well, now you can't use the relational database. There is no one size fits all solution of databases yet. That might be kind of a cool thing for somebody to try to develop. You'd probably become a millionaire or a billionaire pretty fast if you could do that. But the fact is now, and how it is typically in the world, is you've got to use the right tool for the right problem. There's a reason why people who work the trades have a whole toolkit, and then they're a whole garage filled with tool after tool after tool. So it's kind of like that with technology as well. You have to use the right database for the right purpose. So I stopped that video early because I really wanted to make sure that this was easily accessible. And you can kind of, one of the things I probably would go back and ask ChatGPT is, if I don't choose this correctly, what are some problems I could have? But you can kind of just think of it yourself. So like the purpose of a in-memory database is to provide ultra fast data access. So and it's for real time analytics for things like financial trading. So like, what if I accidentally use a key value store? Well, now it's not fast enough. So yeah, so I would go back and say, what is the problem that could occur if I use this database instead of the database that makes more sense to have working for my use case? You can kind of just come up with that with yourself. It's like, the way the data is stored might not be able to be used practically. The speed at which you can interact with the data might be too slow, or it might even be not necessarily too fast, but it might be optimized for speed in a way that presents you with trade-offs that you can't deal with. Like the formatting of the data is now something you can't work with, but it goes 10 times faster. Well, it doesn't matter how fast it is if the format of the data isn't something you can use. So I'll save that quick, just kind of to make that look a little cleaner. And now I'll move on with part 3. So part 3 is real-time streaming ingestion. Real-time streaming data is a particularly tricky type of data to deal with. The stream itself increases the complexity of dealing with the data, and it is possible the stream needs to route to yet another part of the system that it intends to process the data in a streaming fashion. One example of a cloud-based streaming ingestion solution is Amazon Kinesis Data Firehose. See figure 15-5. Okay, so here's the Amazon Kinesis Data Firehose. So I'm not sure. So a hose, you would have water coming in through the tube and then spraying out. So maybe it's similar. We've got machines, then we've got log files, which are async, and they're coming into this centralized point, and then they're coming out as S3, Lambda, Kinesis, Elasticsearch. Here's an example of code that would do that. Notice that Python's async IO module allows for highly concurrent network operations that are single-threaded. Nodes could emit this in a job farm, and it could be metrics or error logs. Alright, so you know what? I think I'm gonna do the examples here. This is, data science sort of stuff, which is always good to have a good handle on. So okay, so I'm here with chapter 14, so I'll go back and I'll make a new one for chapter 15, and I can clean up this. I don't need this. Alright, and I'm going to do mkdir, Python for DevOps, chapter 15, and then move into that. And then I'll do code example.py. All right, and then paste all this in there. And clean it up just using what I know about Python to do all the white spacing and the new lines correctly. And looking in the book makes it pretty clear. Now the white spacing is different here. They have a blank line, and then and then this is not, like, it doesn't appear to be correct, but okay, and then there's going to be more on this line. Okay, so for now this looks good. Now we don't have time imported, so maybe there was something else on here. So it looks like they're missing a module. This is just one of those things where, I have been working with Python for a long time. I've used it professionally for official job functions. So I've been hired to work with Python. I've delivered real professional deliverables using Python. So if you're just kind of, I'd recommend to start with something. This is advanced, is what I'm saying. So if it's not making a lot of sense, this probably isn't the video. There's probably a place to start that's not so advanced. And some of it just is ambiguous. So I don't know if they want all of this to run. Now we've got the loop here. So yeah, I don't know what they want inside it or not. I feel like this is meant to go outside because we can see this is on its own. but we can kind of see what it's doing. Now, if I do an import time, a lot of this down here will go away. So that went away. But now we've got this Firehouse client isn't set up. So yeah, this isn't gonna work. This looks like it's actually might be pseudocode. So maybe it's based on a prior example. Okay, so if I open up the Jupyter notebook that I was working on before, you can look at the notebook here by double clicking on it. Yeah, so no, it's not based on this. So yeah, I think it's just pseudocode. So we'll continue reading. Kinesis data. Kinesis data firehose works by accepting capture data and routing it continuously to any number of destinations. Amazon S3, Amazon Redshift, Amazon Elasticsearch Service, or some third-party service like Splunk. An open source alternative to using a managed service like Kinesis is to use Apache Kafka. Apache Kafka has similar principles in that it works as a pub/sub architecture, and it doesn't explain anything about what that means. So I don't unfortunately know what that means. Let's do a quick check-in with advance the bookmark forward, delete the old one. And then delete this looks like a bug. This bookmark keeps recreating itself. So we'll just delete it again. I'm not sure what's going on there, but it appears to be some sort of bug. So now, so let's go to ChatGPT. Tell me about a PUB/SUB architecture such as like Apache Kafka has.
The pub, sub, publish, subscribe architecture is a popular messaging pattern used in distributed systems to enable scalable and fault-tolerant communication between components. Apache Kafka is one of the most well-known platforms that implements this model. Here's a detailed explanation of how this architecture works, especially in the context of Kafka. Core concepts of pub, sub-architecture, publishers and subscribers. Publishers or producers are entities that create messages and publish them to a message system. Subscribers or consumers are entities that subscribe to receive messages from a message system based on interest in specific topics or patterns. Messages and topics. Messages are the data units transmitted between publishers and subscribers. Topics are categories or feeds to which messages are published. Publishers send messages to specific topics and subscribers receive messages from topics they have subscribed to. Decoupling. The pub submodel decouples the producers of messages from consumers, meaning that neither needs to be aware of the existence of the other. This separation helps in scaling, maintaining, and updating various parts of the system independently. How Apache Kafka implements pub sub. Apache Kafka is a distributed streaming platform that uses the pub submodel with some unique characteristics. Distributed nature. Kafka operates on a cluster of one or more servers, brokers, which makes it highly scalable and fault tolerant. Data is replicated across multiple brokers to prevent data loss. Persistent storage. Kafka stores streams of records, messages, and categories called topics. Unlike traditional messaging systems where once a message is consumed it is removed, Kafka stores these messages on disk and allows them to be reread, enabling high throughput and durable message storage. Consumers and consumer groups. Kafka allows multiple consumers to read from the same topic concurrently. Consumers can be part of a consumer group. If so, each message published to a topic is delivered to one consumer instance within each subscribing consumer group. Consumer groups allow sharing the message processing across a group of processes, instances. Ordering guarantees. Kafka guarantees that for a given topic, messages are ordered within a partition. However, there is no ordering guarantee across different partitions within a topic. Performance. Kafka's performance is effectively constant with respect to data size, so storing data for a long time is not a problem. Apache Kafka is widely used for various real-time streaming data pipelines and applications because of its durability, scalability, and performance. It supports use cases such as real-time analytics, monitoring, event sourcing, and log aggregation.
All right, that kind of went okay. Condice. Okay, so make the explanation more concise. Only use a few sentences, and make it really general and broad and easy for just anyone to understand.
Apache Kafka is a platform that follows the publish, subscribe model, where messages are sent by publishers to topics and received from these topics by subscribers. This system allows for efficient, real-time data exchange and is designed to handle vast amounts of data across many machines, providing reliability and scalability. Kafka ensures that data can be stored and reprocessed if needed, making it ideal for managing streams of data in large-scale applications.
Okay, now to really drive home my understanding, list out the top alternative models and a brief description of them so that I better understand why it is significant that this is a publish subscribe model, because with my understanding, for all I know, everything could be a publish subscribe model, and there's nothing special about Apache Kafka having this characteristic.
Certainly, here's an overview of some common alternative messaging and communication models in distributed systems, alongside the pub sub model used by Apache Kafka. This should help clarify why pub sub is significant and how it compares to other models. Point-to-point queue model. In this model, messages are sent to a specific queue and consumed by a single consumer. It's like sending a letter to a mailbox. Once the letter is taken out, it's gone. This model ensures that messages are processed only once and in the order they were sent. It's often used in scenarios where precise control over the processing order and duplication of messages is critical. Request, response, client-server model. Common in web interactions, this model involves a direct communication link between client, requester, and a server, responder.
That's what
Client
I
sends
know
a request,
about.
and the server provides a response. This is synchronous and typically used in scenarios where an immediate response is required, like in web-based loading or database queries.
Fascinating.
Multicast broadcast model. In multicast or broadcast models, messages are sent to all subscribers simultaneously. This is similar to a radio broadcast where everyone tuned to the channel can hear the broadcast at the same time.
Wow.
It's useful for scenarios where the same data needs to be sent to multiple receivers, but there's no need for message durability or complex consumer management. Event-driven model. This model is based on events where producers generate events and consumers react to them. It can use mechanisms like event queues or event streams. While similar to pub sub, the focus is often more on the state changes represented by events rather than just message passing. It's widely used in modern application architectures to build loosely coupled systems. The pub sub model, especially as implemented by Kafka, is particularly significant because it combines the scalability of the broadcast model with the flexibility and robustness of event-driven architectures. Kafka adds to this a durable storage system that allows messages to be retained and processed asynchronously, providing a reliable backbone for large-scale data processing tasks that few other systems offer. This makes Kafka not just a message transport system, but also a powerful platform for stream processing and data integration.
This was great. I really feel like I understand this now. I wish they would have included the... Okay, so this is great. I feel like I really understand this better now, but I wish you would have included the pub sub model in this. So can you just create a number 5 for the pub sub number model and just have it be included, you know, as just regenerate the output you did before, but just with that same numbered list of the different kinds of models, but include the pub sub model as an entry on the list, please.
Absolutely, let's incorporate the pub sub model into the list for a more comprehensive overview of the different messaging and communication models. Point-to-point queue model. In this model, messages are sent to a specific queue and consumed by a single consumer. Once a message is consumed, it is removed from the queue, ensuring that each message is processed only once by a single receiver. Request, response, client-server model. This direct communication model involves clients sending requests and servers responding. It's commonly used in web interactions where immediate responses are required, such as loading web pages or querying databases. Multicast broadcast model. Messages are sent to all subscribers simultaneously in this model. Similar to radio broadcast, it's useful for sending the same data to multiple receivers at once, but doesn't manage message durability or detailed consumer handling. Event-driven model. Producers generate events that trigger responses in consumers. This model focuses on reacting to state changes rather than just transferring messages, facilitating the building of loosely coupled systems that are responsive to real-time data changes. Publish, subscribe, pub, sub, model. In the pub, sub model, like one used by Apache Kafka, publishers send messages to topics, and any number of subscribers can receive messages from these topics. It offers high scalability and flexibility, allows asynchronous message processing, and supports durable storage, making it ideal for handling large volumes of data and distributing it across many consumers in real time. Including the pub sub model provides a clear picture of its role and advantages in distributed systems, especially in comparison to other models. This model is particularly valued for its ability to efficiently distribute messages to multiple interested parties without requiring direct links between senders and receivers, enhancing both scalability and fault tolerance.
Okay, so I'm ready to move on from this now. So next part is the case study, building a homegrown data pipeline. In the early days of Noah's work, and that's Noah Gift, one of the authors of this book, as CTO and general manager at a startup in the early 2000s, one problem that cropped up was how to build the company's first machine learning pipeline and data pipeline. Whoa, all the way back then they were doing that? A rough sketch of what that looked like is in the following diagram of a Jenkins data pipeline. So Jenkins is a tool So let's see what the diagram looks like. Okay, so this is a Jenkins data pipeline. So we've got time, just as time goes forward. We've got Python aggregation going out to remodeling, going out to deploy. And I'm not sure what they mean by deploy Shiny app. I think they just mean deploy app. They're trying to inject some humor into this, but it just kind of confuses me. Either that or the name of the business was Shiny. But we've got Google Analytics coming in, SQL database, and social media in the early 2000s. That would have been like what is it, MySpace? I forget, but Twitter. It probably would have been Twitter as well, honestly. All right, so the inputs to the data pipeline are any data source needed for business analytics or machine learning predictions. These sources included a relational database, Google Analytics, and social media metrics, to name a few. The collection jobs ran every hour and generated CSV, comma separated value files that were available internally by Apache Web Service. This solution was a compelling and straightforward process. The jobs themselves were Jenkins jobs that were Python scripts that ran. Wait, what? In what year did the Jenkins software get released?
The Jenkins software was first released in 2011. It was originally part of the Hudson project, which began in 2004. The name was changed to Jenkins after a dispute with Oracle, which had acquired Sun Microsystems, the original sponsor of Hudson.
Okay. Was the Hudson project available for like a CTO of a startup to use? Oh, it was?
Yes, the Hudson project was available for use by anyone, including the CTO of a startup.
Maybe that's what he's talking about.
Hudson was an open source continuous integration C tool that became quite popular after its launch in 2005. It was designed to support development teams in automating the processes of building, testing, and deploying their software, making it very suitable for startups looking to streamline their development workflows. Hudson was freely available and could be used by organizations of all sizes to improve their software development practices.
In the early 2000s, how likely is it that somebody might have used it in the early 2000s?
It's unlikely that someone would have used Hudson in the early 2000s because Hudson was first released in 2005.
Right.
Before Hudson, there were other continuous
Who is Noah Gift? Yeah.
Noah Gift is an author, consultant, and educator known for his work in the fields of cloud computing, machine learning, and software engineering. He has a strong background in programming and technology, and he frequently contributes to the education sector by teaching and developing courses related to data science.
Did Noah Gift have a startup in the early 2000s? And ChatGPT does hallucinate. I'm oops.
As of my last update, there is no public record or widely known information specifically stating that Noah Gift founded or was involved in a startup in the early 2000s.
Okay.
Noah Gift is primarily known for his educational contributions, authorship, and expertise in areas like cloud computing, machine learning, and software development, rather than as a startup founder from that period. If you're interested in his career or specific activities during a certain time frame, I'd recommend checking out interviews or biographies where he might discuss his professional journey in more detail.
This is really, really sketchy to me because so first of all, this is not the author talk. Either the author, because Noah Gift is an author of this book, so either he's talking about himself in third person here, which is kind of weird, or like another author is talking about him, which is kind of weird too because he's an author on this book. Why doesn't he just like talk about his own experience? But But it's saying that they were Jenkins jobs. Jenkins didn't exist in the early 2000s. Okay, so I think the startup was named Shiny. In the early 2000s, was there a startup named Shiny?
As of my last update, there isn't a widely recognized or notable startup named Shiny that specifically originated in the early 2000s. However, the term Shiny is well known within the technology and data science communities as the name of a web application framework for R developed by our studio.
Oh, is that it?
This framework, which allows users to build interactive web applications directly in R, was released later around 2012. If you are referring to a different Shiny or have more specific...
I mean, it might have been developing it before it was released. If it was just a small startup, then it would have been, taking them 12 years to release it. That's believable, but this is really odd. I'm sorry. I'm just kind of really... this is kind of breaking my immersion into the book because it does not seem true that they were using Jenkins in the early aughts. The jobs themselves were Jenkins jobs that were Python scripts that ran. If something... And what day is it? It's Saturday, right? Yeah. If something needed to be changed, it was fairly straightforward to change a Python script. When was Python released? If it was released before the early 2000s, what version would have been used at that time? Yeah, 91, I know
Python was first released in 1991 by Guido van Rossum.
Yeah, so like 2.0.
By the early 2000s, Python was already a well-established programming language.
Alright, that's credible that they were using Python, but they weren't using Jenkins. They're either using an analogy saying it was like using Jenkins, or they were using like the Hudson precursor to Jenkins. Yeah, so this is really flowing. There's a reason I stopped reading this book. Let me just say that. And we're almost done, so keep on going here. The jobs themselves were Jenkins jobs that were Python scripts that ran. If something needed to be changed, it was fairly straightforward to change a Python script for a particular job. An added benefit to this system was that it was straightforward to debug. If a job had a failure, the jobs showed up as failed, and it was straightforward to look at the output of the job and see what happened. The final stage of the pipeline then created machine learning predictions and an analytics dashboard that served out dashboards via an R-based Shiny application. And Shiny is we could search for it's part of so Shiny is an open source R package that provides an elegant and powerful web framework for building web applications using R. R is a programming language. The simplicity of the approach is the most influential factor in this type of architecture, as a bonus, it leverages existing DevOps skills. All right, so do that and delete this other bookmark. All right, so serverless data engineering. Another emerging pattern is serverless data engineering. Figure 15-7 is a high-level architectural program of what a serverless data pipeline is. So here's a serverless data pipeline. The final result is to S3, Amazon S3. So we've got Cloud Catch by the hour to Lambda to Dynamo, then to SQS. So these are all AWS services. And then AI AP1. Now let's look at what a timed Lambda does. So we have this here. Using AWS Lambda with CloudWatch events. You can create a CloudWatch timer to call the Lambda using the AWS Lambda console. to set up a trigger as shown in 15-H dash 8. So here's the CloudWatch Lambda timer from the AWS console. Using Amazon CloudWatch logging with AWS Lambda. Using CloudWatch logging is an essential step for Lambda development. Figure 15-9 is an example of a CloudWatch event log. So here we go. Here's an example. It started. It's running. Timestamps. Using AWS Lambda to populate Amazon simple queue service. Next, you want to do the following locally in AWS Cloud 9. Number 1, create a new Lambda with serverless wizard. CD into Lambda and install packages one level up. Next, you can test local code. You can test local and deploy this code. So there we go, Dynamo to SQS. And I'm not going to do this. This depends on interacting with AWS resources, and I was not able to do that without getting charged, so I don't want to take that risk again. This code does the following. Number 1, grabs company names from Amazon DynamoDB. Number 2, puts the names into Amazon SQS. To test it, you can do a local test in Cloud 9. There we go, local test. Next, you can verify messages in SQS as shown in figure 15-11, which is right here. Don't forget to set the correct IAM role. You need to assign the Lambda to an IAM role that can write messages to SQS as shown in figure 15-12. It's got a permission error here. Writing up CloudWatch event trigger. The final step to enable CloudWatch trigger does the following. Enable timed execution of producer and verify that messages flow into SQS as shown in figure 15-13. There we go. Configure timer. You can now see messages in the SQS queue, figure 15-14. Creating event-driven lambdas. With the producer lambda out of the way, next up is to create an event-driven lambda that fires continuously upon every message in SQS, the consumer. The lambda function can now fire in response to every SQS message, figure 15-15. Okay, next step is reading Amazon SQS events from AWS Lambda. The only task left is to write the code to consume the messages from SQS, process them using our API, and then write the results to S3. All right. Yeah, I'm sorry. I can't do any of this because I think they even have... Yeah, I don't have access to these resources unless I create them myself, and anything DNS doesn't fit into the free tier. You do anything with DNS, you're getting charged. But this might not necessarily handle with this, but the point is it's difficult to you can't yeah. You can see that one easy way to download to the files is to use the AWS CLI. So an easy way to download the files, you can do this copy -s recursive, and then you don't have to interact with the GUI or click on anything. So okay, so what did we accomplish? Figure 15-16 shows our serverless AI data engineering pipeline. Okay, so this is what we accomplished. We have the CloudWatch timer set up. 1 minute scheduled job. Then we've got the producer lambda, which reads from the DynamoDB table, puts names into SQS. Event trigger fires every time there's a message. Consumer lambda performs sentiment analysis. That's cool. That's what AI does. And then AWS comprehend puts files into bucket. One of the things I've been wanting to do with this channel actually is convert my long form content, which I have a lot of. Although not if you look at Greg Holt, I think his name is, but my content really isn't that long. It's not 9 hours per video for multiple videos a day. Conclusion. Data engineering is an evolving job title, and it benefits greatly from strong DevOps skills. The DevOps best practices of microservices, continuous delivery, infrastructure as code, and monitoring and logging play a tremendous role in this category, often by leveraging cloud-native technologies. It makes hard problems possible and simple problems effortless. Here are some next steps to continue on a journey of mastery with data engineering. Learn serverless technology. It doesn't matter what the cloud is, learn it. This environment is the future, and data engineering in particular is well suited to capitalize on this trend. Here. I agree with that statement for sure. And the exercises, unfortunately, I'm not going to do these. So the first one is explain what big data is and what its key characteristics are. I think what I might do is have a quick conversation with ChatGPT about each of these exercises and just kind of get the answer.
Big data refers to data sets that are so voluminous and complex that traditional data processing software tools are inadequate to deal with them.
Right.
These data sets typically include masses of unstructured data that need advanced techniques and technologies for organization, analysis, and visualization. The concept of big data is often captured by discussing its key characteristics, commonly known as the 3 versus volume. This refers to the sheer amount of data generated every second. We are talking about sizes ranging from terabytes to zettabytes and beyond. Big data tools are designed to handle this massive volume efficiently. Velocity. This characteristic deals with the speed at which data flows in from sources like business processes, machines, networks, and human interaction with things like social media sites, mobile devices, etc. The flow is massive and continuous. This requires timely processing and handling to generate real-time insights and responses. Variety. Data comes in all types of formats, from structured numeric data in traditional databases to unstructured text documents, emails, videos, audios, stock ticker data, and financial transactions. Managing, merging, and governing different varieties of data is something big data environments are built to do. Apart from these three, additional verses are sometimes included to further define big data. Veracity. This refers to the quality and accuracy of data, which can vary greatly. Big data technology must handle noise, bias, and abnormalities in data. Value. This highlights the importance of turning big data into business value. It's not just about managing large volumes of data, but also about extracting meaningful insights that are actionable and beneficial for the organization. Big data technologies offer powerful capabilities for analyzing data to make informed business decisions and to predict trends and behavior patterns. These capabilities make big data an invaluable resource for companies across various industries, enhancing operations through detailed insights and data-driven decision-making.
All right, so yeah, I'll do this for each of these in the exercises. Right now, I do need a quick break, though, so I'll be right back. All right, I'm back, so let's keep going with these book exercises here. So the next one is what? Okay.
Using small data tools in Python to solve common problems is an effective approach for many scenarios, particularly when dealing with tasks that require rapid development and deployment without the overhead of big data technologies. Python provides a rich ecosystem of libraries and tools that can handle a wide range of tasks, from data manipulation and analysis to more complex machine learning processes. Here are some key tools and how they can be used to address typical problems. Pandas, use case, data manipulation and analysis. Common problems, cleaning data, transforming tables, merging datasets, and performing quick data aggregations. Example, loading a CSV file, cleaning missing values, and computing summary statistics. NumPy, use case, numerical computing. Common problems, mathematical operations on large arrays and matrices, like linear algebra operations or random number generation. Example, creating and manipulating a multidimensional array for a scientific computing task.
Okay, this is actually good. I like this. I like this a lot. You know, I might put a lot of these in the description because I've got some pretty cool stuff coming out of ChatGPT here. All right, so the next one is explain what a data lake is and how it's used. All right, and something's
Taking enormous volumes of data in real time from multiple sources like IoT devices, websites, mobile apps, and more. Analytics and machine learning. With data lakes, you can use tools to perform analytics and machine learning directly on the vast amount of raw data. This can help uncover insights that would be difficult or impossible to derive in a more structured and filtered data warehouse. Uses of data lakes, data discovery and analytics. Data scientists use data lakes to perform data exploration to find patterns or opportunities for deeper analysis. For instance, a data lake might be used to analyze customer behavior across multiple channels. Machine learning. Data lakes allow machine learning models to train on vast amounts of varied data. This broader data set can lead to more accurate and insightful models. Full data retention. For regulatory or analytical reasons, companies might need to store all their data. Data lakes allow the storage of data that is not currently needed but might be useful later without significant cost. Single view of information. Since data lakes can store all types of data, they help in creating a single source of truth for all organizational data, which can be particularly valuable for customer information, asset management, and operational data. Data lakes are a versatile and powerful tool for big data strategies, enabling more flexible, large-scale data operations and deeper analytical capabilities across varied data types. They are particularly valuable in environments where data is voluminous and varied, and where there is a need to quickly adapt to new analytical requirements.
All right, so this is the one I would probably put in my description because these are all tools you can access for free right now and start using. All right, so the next question is explain the appropriate use case for different types of purpose-built databases.
In modern data-driven environments, the one-size-fits-all approach to databases is often not sufficient. Instead, purpose-built databases are designed to solve specific problems or handle specific types of data more efficiently than general-purpose databases. Here's a look at various types of purpose-built databases and their appropriate use cases. Relational databases. Use cases. Traditional business applications for managing data like sales transactions, customer profiles, and financial records, where data integrity and transactional consistency are critical. Example technologies. MySQL, PostgreSQL, Oracle Database. Key value stores. Use cases. Applications that require quick lookups, often with massive amounts of data, where the access pattern is simple read, write-based and key. They are ideal for session stores, caching, and situations where the data relationship is not complex. Example technologies. Redis, Amazon DynamoDB. Document databases. Use cases. Managing semi-structured data like JSON or XML documents. Useful for content management systems, e-commerce applications, and any scenario where each record can have a different structure. Example technologies. MongoDB, Couchbase. Wide column stores. Use cases. Handling large volumes of data across many commodity servers, making them ideal for analyzing large datasets, storing logs, and any application that requires high availability and scalability. Example technologies. Apache Cassandra, Google Bigtable. Graph databases. Use cases. Applications that need to efficiently model, explore, and query networks of connected data, like social networks, fraud detection systems, and recommendation engines. Example technologies. Neo4j, Amazon Neptune. Time series databases. Use cases. Storing and analyzing sequences of data points indexed in time order. Suitable for IoT applications, real-time analytics, monitoring servers, and applications where data is timestamped. Example technologies. InfluxDB, TimescaleDB. Search engines. Use cases. Indexing and searching large datasets of text-heavy information or documents that need to be quickly searched through complex queries, like logging systems or product catalogs. Example technologies. Elasticsearch, Apache Solr. In-memory databases. Use cases. Applications that require ultra-fast response times and can operate entirely from system memory. Commonly used for real-time data processing and high-speed caching layers. Example technologies. SAP HANA, Oracle TimeSyn. Each of these databases is tailored to specific data management needs, offering specialized capabilities that help organizations maximize their data's value in different scenarios. Choosing the right type of purpose-built database depends on the specific requirements of the application, such as the nature of the data, the required speed of data access, the complexity of the data operations, and the scale at which the application operates.
See, this is what I want, is I want a time series database to store and analyze sequences of data points. And I want the data points to be like, where am I going in my apartment? Like, am I always going into the kitchen, like, all the time? Am I never going into, like, the exercise space? Am I never leaving the apartment? And I just want to have, like, after a week, like, this analysis of, like, what I'm doing. I guess might be able to get that with my phone, but, like, I want to have a better, like, I want to have a time series database that I can use to store and analyze my behavior during a day, week, month, year. All right, so then the next one is to build a serverless data engineering Python or pipeline in Python. So let's see what they have to say about that.
Creating a serverless data engineering pipeline allows you to process data efficiently without managing the underlying infrastructure. You can leverage various cloud services to build a scalable, cost-effective pipeline. Here, I'll outline a general approach using AWS services as an example, since it's a common platform for such tasks, with similar concepts applied to other cloud providers like Google Cloud Platform or Microsoft Azure. Components of a serverless data engineering pipeline data ingestion use Amazon S3 for storing raw data. Data can be ingested from various sources using direct uploads, S3 transfer acceleration, or even streamed using Amazon Kinesis. Data processing, AWS Llama, use Llama functions to process or transform the data as it arrives or on demand. Llama can handle tasks such as data validation, transformation, and loading to another system. OzGlue, a managed ETL service that can prepare and transform data for analytics. Use Glue for more complex data preparation workflows. Data storage, after processing, store the transformed data back in S3 or load it into a more structured database like Amazon RDS or DynamoDB, depending on your querying needs. Data analysis and visualization, Amazon Athena, query data directly from files in S3 using SQL, making it highly suitable for ad hoc querying. Amazon QuickSight, use this for business intelligence and visualization. It integrates with S3 and Athena to provide insights into your data. Example Python code for a Llama function. Here's a simple example of a Python Llama function that could be part of a serverless data pipeline. This function is triggered by new files uploaded to an S3 bucket, reads the content, performs a simple transformation, and writes the result back to S3.
Interesting.
Deployment and management deploy. Use AWS CloudFormation or the AWS Serverless Application Model, SAM, to deploy and manage your Llama functions and other resources. These tools help you define your infrastructure as code, making it repeatable and version controlled. Monitor. Utilize AWS CloudWatch to monitor the performance and logs of your Llama functions. This pipeline is highly scalable and cost-effective, as you only pay for the services when they're used. The integration between these services on the AWS platform also minimizes the effort required to manage data flows and infrastructure.
Huh. That's interesting. All right. Well, that's it for that. So next we're on to the case study question. So using the same architecture shown in this chapter, build an end-to-end serverless data engineering pipeline that scrapes a website using Scrappy Beautiful Soup or a similar or a similar library and sends image files to Amazon Recognition to be analyzed. Store the results of the Recognition API call in Amazon DynamoDB. Run this job on a timer once a day. So that's going to cost money, from what I understand. So I'm not going to pay the money to do this. I will feed this into ChatGPT as is, though. And I'll advance my bookmark.
To set up an end-to-end serverless data engineering pipeline that scrapes the website daily, extracts images, analyzes them using Amazon Recognition, and stores the results in Amazon DynamoDB, you will follow several steps. This setup involves AWS Llama, AWS EventBridge, formerly CloudWatch Events, Amazon S3, and DynamoDB. Step 1. Set up AWS Services Amazon S3. Create a bucket to store the images that you scrape. Amazon DynamoDB. Create a table to store the results from Recognition. This table should have a primary key that uniquely identifies each entry, e.g., image ID. IAM role. Create an IAM role for Llama with permissions to access S3, Recognition, and DynamoDB. Step 2. Schedule the Llama function AWS EventBridge. Use EventBridge to schedule your Llama function to run once a day. Set up a rule that triggers the Llama function based on a crowd expression, e.g., at 12 o'clock coordinated universal time daily. Step 3. Implement the Llama function. This function will perform the following tasks. Script website. Use libraries like requests and Beautiful Soup to script website and find image URLs. Download images. Download the images to the Llama temporary storage. Upload images to S3. Upload these images from the Llama environment to your S3 bucket. Send images to Amazon Recognition. Use the Recognition API to analyze the images for specific features or labels. Store results in DynamoDB. Save the analysis results to your DynamoDB table. Here's a Python example using Boto 3 library for the AWS SDK. Step 4. Deployment and monitoring deployment. Deploy this Llama function using AWS SAM or directly through the AWS Management Console. Monitoring and logs. Monitor the execution and performance of your Llama functions using AWS CloudWatch to ensure that the scraping, analysis, and storage processes are running as expected. Additional considerations: error handling. Add robust error handling within your Llama function to manage issues with web scraping, image downloads, or API failures. Security. Ensure that the IAM roles and permissions are strictly managed to prevent unauthorized access. Scalability. If the number of images or the size of images is large, consider breaking the job into multiple parts or using additional Llama functions to parallelize work. This architecture provides a cost-effective, scalable way to periodically scrape web data, leverage powerful image analysis tools, and store useful insights, all without managing any servers.
All right, so that's the end of chapter 15. So I think that's going to be the end of this video. It looks like this next one is kind of story-based reading, which I actually kind of prefer from a book like this because a lot of the examples don't work. I'd rather do an example that's like from a GitHub repo or like somewhere online, so it's like more continually updated. So yeah, I want chapter 16 to be all in its own video. So that's going to be it for this video. And I'll include some of the insights from ChatGPT in the description for the video. But yeah, in the meantime, that's it. Thanks for watching, and see you in the next one.